to understand how to properly apply a variable frequency drive when attempting to use the device to modify conveyor belt speeds. This tutorial will help conveyor operators and designers avoid ruining drive motors when using VFDs to modify conveyor belt speeds. A proper understanding of this topic requires that you understand all rates and all powers. And to verify that the VFD and conveyor drive motor combination is correct, you must compare required power against available power at all relevant rates. Let's take the case of this conveyor belt, which is 120 feet long, 36 inches wide, and it was originally designed to move 450 tons per hour of stone at 330 feet per minute. We calculated separately that the required belt pull to do the job is 2,178 pounds. You can see that handling 450 tons per hour of stone can easily be accommodated within the trough of a 36-inch wide conveyor belt. The power required to do this is 23.6 horsepower. So we install a 25 horsepower motor, and because it's convenient, we use a power supply of 460 volts, three-phase, 60 hertz. The question is, if for some reason we want to reduce the belt speed from 330 feet per minute to half that, can we do that by using a VFD and the existing drive motor? Well, we can check the cross-section and verify that the slower speed will certainly not cause spillage. You can see that the cross-section fills the trough, but you can also see that the required belt pull is 3,760 pounds. Will the drive fail if the VFD is used to decrease the speed to 165 feet per minute? In fact, the answer is it will fail. Required power calculates out at 20.3 horsepower, while available power is only 12.5 horsepower. This tutorial will unwrap that topic and explain such things as relevant rates, relevant powers, and of course conclude with the technique on how to verify drive adequacy. Relevant rates are material handling rate, belt speed, electric motor RPM, and power supply frequency. We'll review why relevant powers are important, what is mechanical power required, what do we mean by electric motor power installed, what does it mean when we select a power supply frequency, and what is electric motor power available. And finally, we'll show the technique on how to compare powers at all relevant rates. Rate is the quantity of something measured against something else. In the case of material handling rate, we usually talk in terms of tons per hour, or in the unit handling industry, we think of packages per minute. Conveyor belt speed selected is a rate, usually referred to as so many feet per minute. Electric motor installed can be referred to as horsepower at a specified power supply. An electrical power supply frequency selected must be defined. Is it going to be constant, or will it vary through the use of a VFD? We'll take a look at 4 different examples, 2 of them in continuous flow applications and 2 of them in metered flow applications. In the case of continuous flow, we will make a given belt speed slower and then check powers, both the required and available. And in the metered flow example, we will make a belt speed faster and check both the required and available powers. Now, in our 2 continuous flow examples, we need to be aware that a constant material handling rate will apply. We're looking at conveyor A, which is feeding conveyor B. In a continuous flow application, the material handling rate of conveyor B is independent of the belt speed of conveyor belt B. If the material handling rate, for example, on A is 450 tons per hour at a belt speed of 330 feet per minute, then the material handling rate on B is going to be 450 tons per hour at a belt speed of 165, for example. The material handling rate does not change. The trick here is, how do we check the power required in the A example? How do we check power available in the A example? And how do we do those same checks with conveyor B? Well, let's look at A more carefully. Let's assume that this application is in Iowa and 460 volt, 3-phase, 60 hertz power supply is convenient and available. So we select that as our electric power supply rate, 60 hertz. We know that we want to move the conveyor at 330 feet per minute, so that's our belt flow rate. We also know that we want to move 450 tons per hour. I've idealized this as a series of boxes, and whether we're talking about so many packages per hour or tons per hour, it doesn't really matter as long as we are consistent in understanding what we mean by material handling rate. We go through the calculations to determine what power is required, and in fact, we decide to select a particular drive system. Drive system can consist of an electric motor, a gear reducer, and some sort of a pulley. If we install the 25 horsepower drive and design it to run on 460 volt, 3-phase, 60 hertz, and the power supply is 460 volts, 3-phase, 60 hertz, then the drive will not fail because required mechanical power is 23.6 horsepower. We're not explaining the techniques on how you would calculate required mechanical power. That's covered in another webinar, but please take it on faith that we've done it accurately. Available motor power is 25 horsepower. Therefore, since 23.6 horsepower is less than 25 horsepower, we have an example where the drive should work continuously, indefinitely. If for some reason we want to decrease the speed, we know that the rate will maintain constant. The material handling rate will stay at 450 tons per hour. Let's explore decreasing the frequency in the electrical power supply. For example, we'll set it at 30 hertz. That will yield a belt speed, 50% of the previous speed, which is 165 feet per minute at the lower frequency. Our material handling rate is constant at 450 tons per hour. The question is, how much electric motor power is available in this circumstance? What is required to drive conveyor B, and how much power is available to drive conveyor B? Well, if we continue with the same motor, 25 horsepower designed to run on a 460 volt, 3-phase, 60 hertz power supply, and we cut the frequency in half, then this drive will fail because required mechanical power is 20.3 horsepower, while available motor power is only 12.5. 20.3 exceeds 12.5, therefore we'll have a failure. We'll elaborate on how to check these things in more detail in the coming minutes. Now let's take a look at our two metered flow applications. In this case, we have unrestricted flow from a hopper, and I point out that material handling rate of this conveyor is linearly proportional to the belt speed. So if we have a material handling rate of 400 tons per hour at a belt speed of 50 feet per minute, for example, if we were to increase the speed in the example on the right, conveyor B, and we set it at 100 feet per minute, the material handling rate will double to 800 tons per hour. How do we go about checking required and available power in the A example? How do we go about checking the required and available power in the B example? Let's look more closely. If we set this drive system to run on a 460 volt, 3-phase, 60 hertz power supply, which is common and available, and we decide that 50 feet per minute will be our design rate to handle 400 tons per hour, we can calculate and select a 20 horsepower drive. What is available, what is required. If the drive selected is 20 horsepower and the supply system power supply is 460 volt, 3-phase, 60 hertz, and the supply is actually at that same frequency, the drive will not fail because required mechanical power calculated previously is determined to be 15.4 horsepower. Available power is 20 horsepower. 15.4 is less than 20. Therefore, this drive should work continuously, indefinitely. Now, however, let's look at an example of speeding up this existing system through the use of a VFD to achieve an 800 ton per hour material handling rate. We said previously that the hopper is unrestricted. We assume that within reason, any material handling rate is achievable simply by increasing the speed of the feeder conveyor. Well, to get 800 tons per hour, we would select 100 feet per minute. We would be tempted to simply connect the drive system to a variable frequency drive and crank in a frequency of 120 hertz. Is the electric motor that has been previously selected adequate to do the job? Let's compare required and available powers. The 20 horsepower drive, in this instance, originally designed to run on a 460 volt, three-phase, 60 hertz supply, if it's connected to a power supply of 460 volt, three-phase, 120 hertz, it will fail because we've calculated separately that required mechanical power will be 29.9 horsepower. However, available motor power is only 20. The ratio that we looked at previously does not apply in this example, and we'll explore that in more detail in the coming minutes. Power is the rate of doing work or the amount of energy transferred per unit time. Why are relevant powers important? And what are these powers? Mechanical power required is generally determined in terms of foot-pounds per minute or horsepower. Electrical motor power installed is usually specified in terms of horsepower at a specified power supply. Electric power supply available may be constant or variable depending upon whether the line voltage, the line's power supply, a 463 phase 60 hertz is used, or a variable frequency drive is used to change the frequency. And finally, what electric motor power is available? Is it going to be constant at a constant frequency, or will various horsepowers apply because various frequencies will be used? These pictures make clear what we're trying to avoid here. This is an example of an AC squirrel cage induction motor used as a conveyor drive. On the right, this is an example where required power exceeded available power. On the left, you see an aluminum motor frame. Within the frame is a stator consisting of copper wire conductors. And within the stator, and by the way, the stator stays stationary, hence the name, the rotor will rotate because as current flows in the stator, a magnetic flux field will be created, which causes the rotor to turn. In fact, this is an example of a 10 horsepower motor, and I can tell you that it's designed to carry and can carry 12.1 amps at full load. This is defined as FLA, full load amps. So the full load amp number that applies to this particular 10 horsepower design is 12.1 when the motor is operating at full load, providing 10 horsepower of power on a 460 volt, three-phase, 60 hertz power supply. The example on the right of a burned motor shows clearly that the motor has been overstressed when required power exceeded available power, and the failure mode here is a generalized burn due to overheating of the stator wires. More current was attempted to be drawn through the stator than the motor was designed to handle. Relevant powers and their importance. If an AC squirrel cage induction motor is used as a conveyor drive, you need to keep this in mind. It's optimized to run at a certain power supply, for example, 460 volt, three-phase, 60 hertz, at a certain FLA, as I mentioned previously. It has no inherent ability to protect itself from current overload. None. That's why external overcurrent protection is needed always. Current overload occurs when required torque exceeds available torque. Saying the same thing in a different manner, we can think that when required belt pull exceeds available belt pull, failure will occur. And finally, when required power exceeds available power. We'll define all of these terms in the coming minutes. Note that current flow in the stator is proportional to the power required from the motor. If the motor is overloaded, then heat from excess current, as you've seen, will cause the stator to burn. If required power exceeds available power, failure. Actual current draw will exceed allowable FOA, failure. Actual stator heat will be beyond the ability of the stator to sustain that heat, failure. Let's define work, and then we'll define power. A constant force of F exerting itself on a point that moves a displacement of S may be used to describe the work done in this instance. Force times distance equals work. Force times displacement equals work, or F times S. And as an example, let's calculate this using imperial units, where work is going to be expressed in foot-pounds. If the force is 1,000 pounds, and it acts along a point in a linear manner, straight line manner, for 330 feet, how much work does it do? Answer, it does 1,000 pounds times 330 feet, or 330,000 foot-pounds of work. 330,000 foot-pounds of work. Now let's define power. We'll define mechanical power. Power is the rate of doing work, or work divided by time. Said differently, it's simply what we just learned, force times displacement per unit of time, or F times S divided by T. So let's continue on with the example mentioned previously. If our force is 1,000 pounds, it exerts itself on a point in a straight line manner for 330 feet, and it takes 1 minute to do that, 1 minute to go 330 feet. Required power equals F times S divided by T, 1,000 times 330 divided by 1 minute. Our answer is 330,000 foot-pounds per minute. Since we know in imperial units that 1 horsepower equals 33,000 foot-pounds per minute, the required power to do this work in this period of time is 10 horsepower. 330,000 divided by 33,000 equals 10 horsepower. We have other video tutorials and other webinars which have been posted on our YouTube channel and our website, which explain the techniques in using SEMA or other methods to calculate required belt pull to move conveyors under certain conditions. We give the equations, we explain the terminology. In fact, we even show how you can avail yourself of free software to calculate what in the case of a bulk example is TE, in the case of a unit handling example, belt pull. Belt pull in bulk applications, as I said, is referred to as TE. In imperial units, this is expressed in pounds. Likewise, in unit handling, belt pull is expressed in so many pounds of force. Looking more closely at the bulk handling example, how can we select an appropriate conveyor drive motor power? Well, simply stated, belt pull times belt speed equals required mechanical power. Let's say that we've calculated that the required belt pull is 1,000 pounds. And let's say that we have selected a conveyor belt speed of 330 feet per minute. The product of these two gives us the required power. 1,000 times 330 equals 330,000 foot-pounds per minute. We know how to convert that into horsepower using this equation. And so therefore our answer is expressed in 10 horsepower, and it comes out to the number of 10. 330,000 divided by 33,000. To simplify this explanation, we've ignored mechanical losses within gears and so forth. We want the math to come out easy so as to have all of the viewers grasp the concepts. So in conclusion, when belt pull has been determined and belt speed has been selected, required mechanical power can be known. And don't forget that when a motor is selected, it's selected to work on a certain power supply. In this example, we're selecting 460 volts, three-phase, 60 hertz. We could just as easily have selected 230 volts, three-phase, 60 hertz. Or we could be doing an application in Europe, for example, at 380 volts, three-phase, 50 hertz. But in our example, we're going to stick with 460 volts, three-phase, 60 hertz. Now let's look more carefully at a synchronous speed of an AC motor. We can define one cycle as 1 hertz. So our current will change polarity from neutral to positive, back through neutral to negative, back to neutral in 1 cycle. And in a typical US power supply, this happens 60 cycles per second. That's why we refer to a system as 60 hertz. So 460 volts divides the voltage, 3-phase divides the number of phases. Another type of power supply could be single phase. We're talking about 3-phase in this example, and we would specify the frequency. Let's look at the components of a typical 3-phase AC squirrel cage induction motor. We have the stator, as you can see here, and we have the motor rotor, as you can see here. This is an example of a 2-pole motor in which we have positive and negative poles indicated in the stator and the positive and negative poles indicated in the rotor to make the explanation more simple. As current flows through the wires in the stator, for example, at 60 hertz, a magnetic flux field is set up, which exerts itself on current which is induced in the rotor, causing it to turn. Since the rotor makes 1 revolution per cycle, if the power supply is at 60 hertz, we would have 60 cycles per second. So the rotor would rotate 60 revolutions per second. So very easily we can see that the rotor RPM in this example of a 2-pole would be 60 times 60, which is 3,600 RPM. Now, to simplify the explanation, we are ignoring motor slip. All of the motors we're talking about in this tutorial are asynchronous motors, which have a certain amount of slip, but we're ignoring that just to make the concepts more easy to grasp. Let's have a look at a real-world example here. We've decided that we want to move a conveyor belt at 330 feet per minute. And we've calculated that the required mechanical power at the drive pulley is 10 horsepower. So we've installed an electric motor of 10 horsepower. If, for example, the pulley has a diameter of 1 foot, we can calculate the circumference by the equation you see here, 2 pi r. And therefore, we can easily calculate pulley RPM using the equation you see here, coming out to be a little over 105 RPM. If we use a 2-pole motor to drive this system in a 60 horsepower supply, as I just explained, the rotor RPM would be 3,600. Speed reduction is nothing more than the rotor RPM divided by the pulley RPM, giving us the appropriate ratio for the gearbox. In this example, we need a ratio of 34.3 to 1. Turning our attention from an exposed drive system to a motorized pulley system, we see the same components as we just discussed. We see a pulley shell of a certain diameter. We see an AC squirrel cage induction motor, in this example 3-phase, and we see a gearbox. We can go through exactly the same rationale. There's no difference. One drive system has an internal drivetrain, the other has an external drivetrain. So if we've calculated required mechanical power at 10 horse, and we're going to install an electric motor, it should be 10 horsepower. We can calculate the pulley diameter in the same manner, coming up with the same ratio. If the motor is two-pole, as in the previous example, we get the same RPM, 3,600, and the gear ratio is the same, 34.3 to 1. The relationship between rotor speed and torque and belt pull will be explained in the coming minutes. But first, let's divert and have a look once again at required power and installed power. We know that required power is work divided by time. So if we have a belt pull of 1,000 pounds and we have a displacement of 330 feet, and we do it in 1 minute, we know that Fs divided by T gives us required power. So 1,000 pounds times 330 feet divided by 1 minute gives us 330,000 foot-pounds per minute, which we can convert to horsepower as I described previously. This example, we have 10 horsepower. Now let's have a careful look at how torque and belt pull may be unraveled. Power equals torque times revolutions per minute times radians per revolution. In other words, you continue with imperial units, that would be foot-pounds, times RPM, times 2 pi per revolution. I also want to, and so therefore torque equals power divided by these terms. Torque also equals force times radius. Said differently, force is simply equal to the torque divided by the radius. So let's have a quick check. If we have a motor of electric, if we have an electric motor with 10 horsepower installed, and we know our pulley RPM is 105 and change, we can calculate that the torque is 500 foot-pounds, 330,000 foot-pounds per minute, divided by the product of 105.04 times 2 pi, 6.2832, gives us 500 foot-pounds. Now we'll do a quick check to make sure that this makes sense. We said that force equals torque divided by radius. If we know that the radius is 0.5 feet and the torque is 500, is the belt pull correct? Yes, because 500 foot-pounds divided by 0.5 feet gives us a belt pull of 1,000 pounds. As we look at an example with a motorized pulley, you can see that a belt pull of 1,000 pounds at a belt speed of 330 feet per minute will yield a power requirement of 10 horsepower. And you can see that the installed power at the drive pulley is exactly as explained previously. Now let's drill down to rotor RPM and rotor torque within the product itself. Whether it's an exposed system or motorized pulley system, the concepts are identical. If the installed motor power is 10 horsepower and the RPM is 3,600, we can easily calculate that torque equals 14.59 foot-pounds by dividing, as you see here, 330,000 foot-pounds per minute divided by the product of 3,600 and 6.2832. Pulling it all together, you can see that installed torque with a 10 horsepower motor is 14.59. Required mechanical torque at the pulley face is 500. The reduction we said previously in the gears would be 34.3 to 1. So you can see that motor torque times gear reduction equals pulley torque. 14.59 times the gear reduction equals 500 foot-pounds. Continuing to pull all of this together, I need to point out that in an asynchronous AC squirrel cage induction motor, motor torque is nearly constant over the allowable frequency spectrum. I'll define that in a minute. And motor power is linearly proportional to the power supply frequency. Let's have a look now at a variable frequency drive take some of the mystery out of it, and then apply it to understanding conveyor drive motors. A variable frequency drive is a frequency converter. It uses pulse width modulation of voltage to change the power supply frequency in the current. It varies belt speed by changing the frequency, as I said previously. It also enables a three-phase motor to be applied on a single-phase power supply simply by modulating the pulse appropriately. Let's call it a black box. It does it in a very amazing way. I'll show you a curve in just a second. Here are a couple of VFD do's and don'ts. You can count that, you can depend on the fact that an AC squirrel cage induction motor, such as we're discussing here, will provide a torque of 95% of full torque or more within the allowable spectrum. Years ago, we used to say, please restrict yourself to a frequency spectrum of 12 hertz to 66 hertz. But nowadays, since flux vector VFDs are very common, that limited frequency spectrum has gone away. It's possible to have a much wider frequency spectrum. However, it must be done in a manner that we're describing here, where required power at all rates is checked against available power at those same rates. And one last thing in closing on VFDs is that we recommend that if you're going to install the VFD more than 30 feet from the motor itself, you should filter the output. And nowadays, VFDs have built-in filters, so it's no longer necessary as it used to be to make sure that an extra filter was added. The filter will prevent the problem of frequency-induced voltage spikes, resonant frequency-induced voltage spikes. Now let's have a look at pulse width modulation. As you can see in this graph, the voltage source is pulsed using a certain clock frequency. Here we're looking at 20 milliseconds, and the voltage source is modulated electronically as a series of pulses. Here's a longer pulse, a very short pulse, shown on the blue bars. Matching these voltage pulses are a sine-like, or the result of these voltage pulses is a sine-like current shape, sine-like current shape as current flows from neutral to positive, back through neutral to negative, back to positive again, by modulating the voltage pulses. And perhaps it's obvious, but let me state that a variety of variable frequency drives are available, and the clock frequency built into the VFD can vary from some are available with clock frequencies as low as a few kilohertz, and some have clock frequencies as much as a couple of megahertz. The point being, the higher the clock frequency, the smoother the shape of the curve of the power supply current. Now let's review the topic of motor power and motor current draw. The illustration before you shows the relationship between horsepower and FLA, full load amps. You can see pictured here the 10 horsepower AC squirrel cage induction motor we described previously. This one is designed to provide 10 horsepower and will have the ability to handle 12.1 full load amps at full load. In other words, when the motor is working at the power supply frequency for which it was designed, 460 volt, 3-phase, 60 hertz, working at full load, providing 10 horsepower, it will draw continuously 12.1 full load amps. We have another motor that has been designed to run on 460 volt, 3-phase, 60 hertz, and provide 20 horsepower. However, note that this one is designed to carry continuously 23.6 full load amps. If a 10 horsepower motor is subjected to a mechanical overload in which it is expected to provide electrical power of 20 horsepower, while it was designed to only carry 12.1 full amps while providing 10 horsepower, it will burn. The current carrying capacity of the stator will be exceeded. And as you can see, while we would have a success if the motor continuously provides 10 horsepower, we will have a failure if that same motor attempts to provide 20 horsepower. Now let's wrap up our tutorial and look at how to verify drive adequacy. We will explore the two continuous flow cases that we mentioned at the beginning of this tutorial and follow up with an exploration of the two metered flow cases we discussed at the beginning. We're going to compare required power and available power both at the initial design rate and at all relevant rates. Case 1. I remind you we looked at conveyor A, in which the design parameters were as follows. We wanted to move 450 tons per hour at a belt speed of 330 feet per minute on a power supply of 460 volt, 3-phase, 60 hertz. We decided to install a 25 horsepower motor, which was designed to run at 460 volt, 3-phase, 60 hertz. We have calculated separately that the belt pull with this set of parameters is 2,360 pounds. It's necessary to provide an effective tension of 2,360 pounds. Since the design speed is 330 feet per minute, the product of belt pull and belt speed divided by 33,000 yields the required power, which is 23.6 horsepower. If we install a 25 horsepower electric motor designed to run at 460 volt, 3-phase, 60 hertz, and we actually run it at that power supply frequency, obviously the available power is 25 horsepower, and that exceeds the required power of 23.6. This is a successful application. However, if we decide to slow down the conveyor by using a VFD to decrease the power supply frequency, we will have a failure, as was mentioned previously, and here's how to understand it. We calculated separately that the belt pull is 4,060 pounds to handle 450 tons per hour at a belt speed of 165 feet per minute. We know that the product of belt pull and belt speed divided by 33,000 yields a power requirement of 20.3 horsepower. We have installed a 25 horsepower motor, which was designed to run at 460 volt, 3-phase, 60 hertz. However, we have attempted to use a VFD to slow down the supply frequency to 30 hertz to slow down the conveyor belt. Notice that motor power is no longer available at 25 horsepower. In fact, if we multiply 25 times 30 hertz and divide by 60 hertz, you can see that the available power is only 12.5 horsepower, and this would be a failure. The motor would be overloaded. What do we do about this situation? Well, here is what we suggest. Take a look at conveyor B and solve that problem, then go back and check to see if the correction also works on conveyor A. So we're going to look at the exploration of a new drive motor for conveyor B, rather than the original 25 horsepower designed to run at 460 volt, 3-phase, 60 hertz. We are going to install a 50 horsepower motor designed to run at 460 volts, 3-phase, 60 hertz, use a VFD to decrease the power supply frequency to 30 hertz. Let's see what power is available. 50 horsepower is what we have installed. We decrease the frequency to 30 hertz. 50 times 30 divided by 60 yields an available motor power of 25 horsepower. Since 25 horsepower is higher than 20.3 horsepower, this is a successful application. Now let's go back and check the A conveyor parameters. If we leave our 50 horsepower installed, and it has been designed to run on 460 volt, 3-phase, 60 hertz, and we use that exact frequency, of course, we're going to have 50 horsepower available. 50 horsepower exceeds the required power of 23.6. and we will have a successful application on the A parameters. So conveyor A and conveyor B will both be able to run continuously, indefinitely with this setup. Now let's explore the two metered flow applications. I remind you that we decided to attempt to increase the conveyor speed from 50 feet per minute to 100 feet per minute, and we failed. So if we are moving 400 tons per hour at 50 feet per minute, and we've installed an electric motor of 20 horsepower, which was designed to run at 460 volt, three-phase, 60 hertz, we've calculated separately that required belt pull for the conveyor feeder would be 10,164 pounds. The product of belt pull and belt speed divided by 33,000 tells us that required power is 15.4 horsepower. We've installed a 20 horsepower. I'm further defining the drive as consisting of an 8-pole motor with a 2-foot diameter drive pulley. We use a power supply of 460 volt, three-phase, 60 hertz. And of course, we have available to us 20 horsepower, which exceeds 15.4 horsepower at the 460 volt, three-phase, 60 hertz power supply, a successful application. Now, here is why it's impossible to increase the frequency significantly beyond 60 hertz. Notice that we've calculated on the faster belt, we define this as conveyor B, we want to increase the belt speed from 50 feet per minute to 100 feet per minute because we want to move 800 tons per hour. We calculate through these parameters that a belt pull of 9,867 pounds is required. Belt pull times belt speed equals the required power, as we said previously, 29.9 horsepower. We have installed a 20 horsepower, which has been designed to run at 460 volt, three-phase, 60 hertz. Remembering that we're talking about an 8-pole motor in this example and a 2-foot diameter pulley, we can calculate that the rotor RPM is 900 at 60 hertz. We can calculate gear reduction required is 113 to 1, and rotor torque is 116.7 foot-pounds. Now watch what happens. If the rotor torque is 116.7 foot-pounds, and we attempt to increase the rotor RPM by changing the power supply frequency from 60 hertz to 120 hertz, we cannot get 1800 RPM because 116.7 foot-pounds of torque times the ratio of 120 divided by 60 times the RPM of 900 times 2 pi per rev tells us that this motor would provide 1.3 million foot-pounds per minute of power, which is impossible. That equates to 40 horsepower. As was explained previously, the motor stator will burn because it cannot carry the current required to sustain that kind of magnetic flux to turn the rotor. So we have a failure. The available power is 20 horsepower and not 40 horsepower. Since the required power of 29.9 is higher than 20, we have a failure. What can we do? Let's look at the selection of a new drive motor for conveyor B. Let's select a motor with a power of 40 horsepower designed to run at 460 volt, three-phase, 60 hertz. Since the installed motor power is 40 horsepower at 60 hertz, and we run it at 460 volt, three-phase, 60 hertz, available power is 40. 40 is higher than 29.9, therefore we have a success when we attempt to run the conveyor at 100 feet per minute. Now we need to go back and check to see that this drive is adequate in the conveyor A case. This is the case in which we want to run the conveyor at 50 feet per minute. The motor power is now 40 horsepower, designed to run at 460 volt, three-phase, 60 hertz, but we're going to use the variable frequency drive to slow down the frequency from 60 to 30 hertz. Let's see what motor power is available to us in this case. It's designed to provide 40 horsepower when running at 60 hertz. The power available when running at 30 hertz is 40 times 30 divided by 60, or 20 horsepower. So the available power when driving the conveyor at a slower belt speed, the power is 20 horsepower. This exceeds the required power of 15.4, and the application will be a success. In this tutorial, we have discussed relevant rates, relevant powers, and how to verify conveyor drive adequacy against a variety of rates. We hope you found this tutorial useful, and I would encourage you to check out our YouTube channel. This would be the Womeka Corporation YouTube channel, or visit our website for more conveyor drive design and maintenance tips. And you can use the convenient links that you can see before you on your screen. Thank you very much.